Hello everyone, my name is Rayna Hata and I am part of the 2022 RISC program. I am a rising senior at Colby College studying computer science with a minor in Japanese. This summer and last summer, I had the opportunity of researching with Dr. Isaac Isukapati, Dr. Zachary Rubenstein, and Dr. Stephen Smith at the Intelligent Coordination and Logistics Lab. My research centered around blind pedestrian localization and path prediction at urban crosswalks via ultra-wideband devices. First, let's talk about the motivation. Studies found that those with visual impairments find navigating crosswalks in urban settings difficult. They find that some intersections are hard to understand due to the lack of clarity in crossing time or signal status. Some spend multiple cycles to understand the intersection before crossing. This can lead to a significant loss of time. Furthermore, multiple factors such as other pedestrians and vehicles, unclear crosswalk cues, or loud noises can all cause a blind pedestrian to drift away from the bounds of the crosswalk. Thus, we propose a method for blind pedestrian localization, path prediction, and reorientation to help those with visual impairments safely and efficiently complete their crossing using a smartphone and ultra-wideband devices. To do so, we first had to ask these three questions. Can we track a pedestrian while they are on a crosswalk? Can we detect if the pedestrian is drifting out of the bounds of the crosswalk? And finally, can we reorient them to bring them back safely into the crosswalk? This research was first started by Dr. Smith and his team with the creation of Petpal. Petpal is a smartphone app designed to promote safe intersection crossing for pedestrians with disabilities. It will continuously communicate directly with the traffic control system at the intersection to inform the pedestrian of the crossing status. It also knows the speed at which the user travels and communicates their crossing constraints to ensure a sufficient crossing time. But in order to achieve our goals, we first had to improve the localization tracking of Petpal. Petpal currently uses Bluetooth, which has a greater error with tracking pedestrians. Thus, we implemented ultra-wideband devices to replace the Bluetooth. We field-tested UWB devices to ensure that the accuracy fit to the needs of Petpal. In order to do so, we tested a set of 4 iPhones, all of which have UWB chips, and utilized them as corner beacons. Then, we tested if they were able to detect both the arrival at the intersection corners and the completion of the crossing trip. They showed an accuracy of up to a few centimeters, up to a distance of 60 feet, which is enough to fit to the needs of Petpal. After ensuring that the UWB devices were accurate enough, we implemented the pedestrian localization algorithm. First, the pedestrian is detected at the crosswalk by both ultra-wideband anchors. The first anchor is located at the beginning of the crosswalk and labeled as A1 in the image, and the second is located at the end, labeled as A2. At each time interval, a distance measurement between the anchor and the pedestrian, as well as a distance measurement between the second anchor and the pedestrian, is taken. Now we have 2 distances and no distance between the 2 anchors, which allow us to use the cosine rule for finding angles. These angles represent the angle that the pedestrian is located during the current step with respect to anchor 1 and anchor 2, labeled as A and B in the image. They will help determine the pedestrian's geolocation calculated from each anchor. Then to determine the final geolocation, we take the average of the 2 readings. This process is repeated each time until the crossing is complete. After the localization, the path prediction algorithm takes the following steps to estimate if the pedestrian will drift off the bounds of the crosswalk if they continue their current path. First, using the localization coordinates, we calculate the slope relative to the initial position. Then we will store J number of slopes in a heap queue to take the median of those slopes so that at any given time step there will be a median computed with the number of slopes. The reason we take the median is to ensure that no outlier readings can throw off the direction that we think the pedestrian is going in. The median of the first J slopes that we take will be known as the reference slope. Any medians taken after that will be compared with the reference slope. If the current median slope is out of the threshold bounds of that reference slope, we will flag that reading as a potential information that the pedestrian may be heading in a direction that will lead them out of the bounds of the crosswalk. If the algorithm finds that the pedestrian is moving in a slope outside the threshold of slope we want them to be at, then we will jump into the reorientation part. We will wait to give instruction to the pedestrian until they have been moving out of the bounds 5 times in a row. Much like the reason why we take the median, we want to make sure that we are not reacting to one faulty reading. It is important to make sure that we are confident that the pedestrian is drifting before giving them instructions. Once they have been out of the bounds for 5 time steps, we will instruct them to turn right or left while they keep walking. The algorithm will continue to give directions until the pedestrian slope is back in the bounds of the threshold that we want them to be at. While the UWB devices were field tested, the algorithm was tested in a simulation setting using SUMO, which stands for Simulation of Urban Mobility. We implemented scenarios where the pedestrian will drift upwards or downwards towards the bounds of the crosswalk. The top image shows the crosswalk that is implemented in the SUMO simulation based off of the intersection shown in the bottom image. Shown here is the result of our localization of the pedestrian. We saw that the pedestrian was localized with an accuracy of 0.03% error from the ground truth, which is the blue line, and the orange line represents the estimated location at each time step. The green line represents the upper bounds of the crosswalk, so at some point you see that the pedestrian has crossed over the bounds of the crosswalk. The 2 images below show the path that the pedestrian would have taken if not corrected, which is shown in the blue line, and the path that the pedestrian took when they had been corrected by the algorithm, which is shown in the yellow. As you can see, the lines are the same until the pedestrian is detected at going at a slope that you don't want them to go at and corrected to go straight. Some of the future work that we would like to do is to implement inertial measurement unit sensor data to further accurately predict the drift. And then we would also like to implement more ways a pedestrian can drift away from the crosswalk and not just them starting at a correct path and then starting to drift to the end. And lastly, we would like to field test the algorithm. Thank you to Dr. Sugapati, Dr. Rubenstein, and Dr. Smith for their support and mentorship throughout the summer. Also, thank you to Rachel Burson and Dr. John Dolan for organizing the summer program. And lastly, thank you to the RISC program sponsors who made this program a possibility.